Okay, so last week we had started with the module called as waveguides. So first we started with what? Which type of waveguide? It was parallel plane waveguide, right? And we studied that there is some term comes cos theta is m lambda by 2d. I'm not sure of the formula. It might be m pi by beta, and which is also equal to m pi by beta d. So we said, and this is the point where the electric fields become zero. So we have the usual z axis, and this is the z axis, right? So electric field, we saw it becomes zero at lambda by, and lambda by, if you take d here, it becomes m lambda by 2 cos theta. So it becomes zero at every lambda by 2 cos theta, right? So you can place a conducting boundary at every lambda by 2 cos theta. So that is how a parallel plane waveguide exists or comes into picture, right? So this is how we treated parallel plane waveguide. Then we said there are two modes. One is TE mode and one is TM mode, right? Why it is called as TE or transverse electric mode? Because the electric field is transverse. Only the electric field, in fact, is transverse to the direction of wave propagation, right? And why is it called as TM? Only the magnetic field is transverse to the direction of wave propagation. That is, here you get electric field as Y component. Let me just check. It is Y component only. Yeah, it is Y component only, and H you get as what? X component and Z component. So magnetic field is in the direction of propagation, but electric field is not in the direction of propagation, but it is in the direction of Y, and Y is perpendicular to the direction of propagation, which is Z. So electric field is transverse to the direction of propagation, hence called as TE mode. Here magnetic field is transverse to the direction of propagation, hence TM mode. And further, for TE mode, what we studied? TE0 does not exist, and TE1, TE2, etc. exist. What we studied for TM mode? TM0 exists, right? And then we studied TM1, TM2, etc. also exist, right? So this was the main difference, right? So let me just write the TM mode equations again. So the total electric and magnetic fields of a parallel plane waveguide, for which mode? TM mode I am writing. For TM mode are given as, what are they? E1 vector equal to 2j E I naught sine of m pi x by d e raised to minus j e raised to minus j beta z y cap. No, these are for T mode, sorry. Again, as I told you, you don't have to buy out these equations. These are just for understanding. So I am first making the concepts clear. That is why I am writing all the equations. So you don't have to buy out these equations. And I'll tell you what will be asked in the exam. So you don't worry about that. So what was I doing? I was writing the equations for TM mode, right? So I have them. Obviously, I am referring from the book. So E1 vector equal to 2j ei naught sine of m pi x by d e raised to minus j beta z m pi by beta 1d z cap plus 2 ei naught beta by beta 1 cos of m pi x by d e raised to minus j beta z x cap. This is what E1 vector. Let's write H1 vector. So H1 vector is 2 ei naught upon eta 1 cos of m pi x by d e raised to minus j beta z y cap. Right? So these are for what TM mode. So again, if you have not understood, I will tell why this tells us that it is a TM mode. So if you see, H vector is having what y cap, and E vector is having what z cap and x cap. So again, how we had assumed the diagram, reflection diagram at the start. This was z, this was x, and y was coming out. That is towards the camera or towards you, and the wave was incident in this direction with an angle theta. So it got reflected in this way, and we had used parallel polarization, right? So this was hi. So if thumb is pointing in the direction of wave propagation, my curled fingers give direction from E to Z. So H is above, so E to Z, so E should be like this. So this is my EI. Similarly here it should be like this. So this is ER. So this is HR, right? And this is medium 1, this is medium 2, right? So obviously this was what a conductor. So we have seen in electromagnetics course that electromagnetic wave cannot penetrate a conductor, so entire wave gets reflected, right? A very small portion might penetrate. That concept is what skin depth. So 37 per, but even though it penetrates, it will be only of the order of micrometers. Why? Because skin depth delta is 1 upon square root of pi f mu sigma, and usually we will have very high frequencies, so delta will be in the range of micrometers only, right? And how is it defined? It is defined as the amplitude of the electromagnetic wave will decrease by 1 by E, that is around 37%. So maximum, if you go 3 times 37, it will be more than 100%. So maximum 3 times it will get exponentially, it will deteriorate. So we'll not go there. So what was I saying? I was trying to tell you why we call it as TM mode. So this is my Z direction. So wave is traveling along the Z direction, right? But is traveling along Z. So electric field is only in Y direction, right? So electric field is oriented like this, that is towards you. This is Y direction, fine. But if you see electric field, magnetic field, sorry, is oriented in Y direction. Electric field is in the direction of propagation and as well as in X direction, like this. So electric field is like this as well as like this, right? So it is traveling like that. But H vector, how is it? It is oriented only in Y direction. So it is perpendicular to the direction of propagation, right? Now you might say, sir, X is also in the direction of, perpendicular to the direction of propagation. But you observe E is also in the direction of propagation. That is not the case with H. So that is what we can say. A magnetic field H vector is perpendicular to the direction of propagation. That is, it has only one component in the perpendicular to the direction of propagation. There is no component which is in the direction of propagation, right? So that is why it is called as transverse magnetic mode, abbreviated as what? TM. Why transverse? Because transverse means perpendicular, right? So that is why it is called as transverse magnetic mode. And again, why we said TM0 exists? Why we said TM0 exists? If you substitute m equal to 0, this term goes to 0. If you substitute m equal to 0, this term exists. So E is present. A tick mark indicates it is present. Let's see H. So if you substitute here H, cos 0 is 1. So this term also exists. So H exists, E exists means the mode exists. That is, the electric fields exist. If you observe for TE mode, what was happening? The electric field was vanishing, but you are getting H vector. Then we had an argument that if electric field is not there, obviously from our basic electromagnetic course, magnetic field cannot be there, because we have seen from Maxwell's equations that for a time varying electromagnetic field, there will also always be an associated magnetic field and vice versa. So we said if E is not there, H will also be not there. So that was the case for m equal to 0 for TE mode. So that is why, since the fields did not exist, TE0 mode does not exist. But if you substitute m equal to 1, 2, etc., those mode exist. So that is the thing here. So this can be very useful Viva questions. Right? So what else I had to discuss? Yeah. So about from this, we had one more equation. So that was beta equal to beta 1 square root of 1 minus m lambda 1 by 2d the whole square. Right? This was our propagation constant. Again, why is it called as propagation constant and why not phase constant? Because in a waveguide losses are very low. So gamma is alpha plus j beta. Since losses are low, you can ignore alpha. So gamma is what? Nothing but j beta. Right? So and gamma is called as what? Propagation constant. So you are getting only these terms. That is why it is called as directly propagation constant. To be strictly speaking, it is called as modal propagation constant. So again in Viva, someone might ask you, the examiner might ask you what is modal propagation. So how will you answer? You can answer in this way that in the waveguide, the electromagnetic wave travels in the form of modes, which are TE and TM modes, which indicates that the wave can be launched only at some discrete angles of theta. So this particular discrete angles of theta are designated by TE and TM modes, which is called as modal propagation. So that propagation happens only due to this mode. Okay. So now let's consider. So next we studied about frequency, cutoff frequency, and dispersion. What was cutoff frequency? FC. We said that it is the minimum threshold frequency above which the wave will start to propagate. So if we say cutoff frequency is 3 gigahertz. So if you launch a wave, if you try to launch a wave which is having a corresponding frequency of 2 gigahertz, let it be at any angle. What will happen? It will not be able to propagate inside the waveguide. Why? Because the cutoff frequency of the waveguide is 3 gigahertz. So that is what is meant by cutoff frequency. Next we studied dispersion. What is dispersion? We said that the phase velocity was dependent on frequency or omega. That is, the frequency changes, phase velocity changes. So that is, waveguide is a dispersion medium. And what we said that for air, Vp is omega by beta, and beta is what? Omega root mu epsilon. So omega gets cancelled, you get 1 upon root mu epsilon. So air is non-dispersive because it is not dependent on frequency, right? But what happens in a waveguide? You have the conducting boundaries. Inside you have air only. So even though air is non-dispersive, but the medium itself is, that is the waveguide itself is dispersive. So that was what we discussed. Apart from this, we also discussed that wave cannot be launched at theta equal to pi by 2. Why? Because again we saw in TE mode, m equal to 0. If you substitute there, you will observe that m equal to 0 corresponds to theta equal to pi by 2. So wave cannot be launched at perpendicular angles. Okay. So this is what we studied in last lecture. So let's study one more topic related to parallel plane waveguide. It is TEM mode. So it is nothing but transverse electromagnetic mode. So we have already touched upon this in electromagnetics course. What were we saying? We were saying that if electric field is oriented in x direction and magnetic field is oriented in y direction, we had a pointing theorem. What is pointing theorem? Denoted by P vector. It is E vector, this is also vector, cross H vector, right? So pointing vector is E vector cross H vector. So E vector is in x direction, cross with y vector. What will you get? P vector is in which direction? Z direction. Means if you have a x cap, you have y cap, both are perpendicular. So I can represent in this way. So electric field is in along, let's say this is x, this is y. So electric field represented by red sketch pen is along x direction. Magnetic field represented by brown sketch pen is along y direction. What happens? The cross product will always gives us what? The direction of perpendicular plane. Right? So this is my plane, direction which is perpendicular to this plane. This is x, this is y. It will be what? Z cap. Right? Means what is happening? So electric, and we had proved that E vector and H vector are perpendicular and they constitute a wave. So it is an electromagnetic wave. Right? And we concluded that it is traveling. So it is traveling in which direction? Z direction. So we have transverse, that is this thing's perpendicular, and we have electromagnetic wave. So that's why the wave was called as what? TEM wave. Remember, we are not studying TEM wave now. We have already studied. We are studying something called as TEM mode. So now this is very light, so I'll change the pen. So transverse electromagnetic mode. So let's see what is this mode. So let's again go to TM mode equations. Right. So this is E1 vector, this is H1 vector for TM mode. So let's substitute m equal to 0 in equations of TM mode of parallel plane waveguide. So you substitute m equal to 0. Let's see what we get. So E1 vector equal to, what will it be? This is 0. So entire z cap will go to 0. But you have a x cap term also, right? So it will be 2 ei naught. Before this, what will be beta? I have written beta also. So m equal to 0. What will be beta? Beta equal to beta 1. So I'll write that here. Beta equal to beta 1. Right? For m equal to 0. So this will be what? Beta upon beta 1, 1. And cos 0, this is 1. So 2 ei naught e raised to minus j beta z x cap. This is what? E1 vector. Similarly, what will be H1 vector? So 2 ei naught upon eta 1 as it is. 2 ei naught upon eta 1. Where is it? Yeah, cos m is 0, so cos 0 is 1 maximum value. So this is also as it is. Then e raised to minus j beta z y cap. Okay, so this is H1 vector. So what do you observe? So just think over it. We have E vector as x cap. We have H vector as what? Y cap. Right? Correct? And what is happening? How is the wave traveling? Wave is again traveling in which direction? Or I can say power is traveling again in Z direction. So again, this is what? Transverse electromagnetic nature. So this mode is called as what? TEM mode. So this mode corresponds to these equations, right? And what we have substituted? We have substituted m equal to 0. So m equal to 0 corresponds to which mode? TM0 mode, right? So TM0 mode is nothing but our TEM mode, right? So what we are seeing? TM0 is nothing but TM mode. And since m equal to 0, means it has no cutoff frequency. So any arbitrary frequency can propagate in this mode. Again, why any arbitrary frequency? Because m equal to 0. Since m equal to 0, you are getting no frequency terms here because there is m equal to 0. If you calculate E1, you are getting no frequency terms. Again in H, you are getting no frequency terms, right? So that is why any arbitrary frequency can travel in the waveguide which supports TEM mode. So we say because of that, since it is not frequency dependent, so TEM mode is what? Non-dispersive. Okay. So this is a very important thing. It can again be a Viva question. Now there is one very interesting thing here. You just take the ratio of E and H. You take E and H magnitude obviously. What you will get? 2i naught, 2ai naught will get cancelled. This will get cancelled. And what you will get? It is nothing but eta. And eta we have seen in basic electromagnetic course. It is 377 ohms. Right? Means what is happening? This TEM mode is nothing but what? Same as the wave which was traveling in an unbound medium. Unbound medium means what? It was just having one conducting boundary, not even one conducting boundary. For example, if I have an antenna, a wave is getting transmitted from the antenna. It was traveling at what? It was facing an impedance of 377 ohms. Same is happening. Means whatever is happening is same happening as in an unbound medium. This is an unbound medium, right? Air is an unbound medium, right? Because it is open. But now what is happening? We have two conducting boundaries. It is a bounded medium now, right? And same thing is occurring inside. So the question is, if you think a bit deeper, you might say, how are the boundary conditions satisfied? Because we always stress on boundary condition. We always stressed on electromagnetic course that boundary conditions should always be satisfied. How are they satisfied here? So let's see that. E vector is in which direction? X direction. So according to this diagram, E vector is exactly perpendicular to the conducting boundary, right? For H vector, I will use green pen. It is coming out of the paper since Y direction. So here also x is like this, z is like this, so y is like this, right? And how is the wave traveling? Like this. So what is happening? M equal to 0, right? This we have done for m equal to 0, right? And what is the value of m? M is 0, right? Means there are no variations of electric field. So means no variations means whatever is the field here, that will be here, right? No variations means this entire value it is constant. So here also it is 0, here also it is 0. Means the tangential components are what? Equal. So 81 equal to 82, right? And they are 0. That is the tangential components are 0. Similarly, you can see that you can think over it that normal component are also satisfying the boundary conditions. Okay. So in this way, it is satisfying the boundary conditions. So that is why TEM wave can also travel inside a waveguide. And that is the reason these are used in our coaxial cables, which supply our DTH and Hathway cable, etc. Right? So coaxial cable supports TEM mode. Again, this can be a Viva question. Okay, and what is the important thing about them? They are non-dispersive. Okay, and one very important thing before closing the lecture, what we saw in that page, yeah, T0 does not exist, right? So T1 exists. So this is the one having what? Minimum cutoff frequency, right? Then this has the next higher, and so on for 3, 4. Then for TM mode, this is having the minimum cutoff frequency, right? So whichever modes are having the minimum cutoff frequency are called as dominant modes. Okay, so always, so you might be asked a question in Viva again, what are dominant modes? This can also come as a question number 1 compulsory part in your final exam. What are dominant modes? Define dominant modes or give the examples of dominant modes for TEM modes for a rectangular waveguide or parallel plane waveguide. Okay, so this is the way you have to answer. Okay, so next lecture we'll start with rectangular waveguides.